Welcome to Unsaturated Polyester Resins Part 2. This is where we're going to talk about the various polymerization steps to get you from the monomers that we talked about, mixed with reactive diluents, to a cross-linked thermoset. There's actually two different polymerization processes that go on here. The first one is a polyesterification reaction, and what you're doing is you're creating the polyester, alkyd, in this particular step. Now the alkyd is just the polyester portion of this resin. A full unsaturated polyester resin consists of the UP-alkyd and the reactive diluent. So this is in the first step where we're doing polyesterification. We're creating the unsaturated polyester alkyd. So aside from just creating polyesters or ester bonds, you can get four side reactions during this. The first one being isomerization of malleate to fumarate. I'll explain that later. Addition of glycol to the malleate or fumarate double bonds, oxidative destruction of double bonds, and loss of glycol. Reactions 2 through 4 are not good for the final resin. Reactions 2 and 3, in other words, addition of glycol to the double bonds or oxidative destruction of double bonds, reduces the overall resin's ability to cross-link. You need that olefinic unsaturation to persist through the polyesterification, otherwise you can't cross-link it later on. And reaction number 4, you're losing one of your monomers, so that reduces your molecular weight, so you have a weaker polymer. However, reaction 1 is not detrimental. In fact, it's actually desirable, and that's why certain glycols are chosen instead of others, and I will go on to explain that. So this is isomerization of malleate to fumarate. So this is maleic anhydride. This is a cis isomer, and that, through a particular process, can turn into this fumarate isomer. Now this is an anhydride, but you can open this up and this will create a carboxylic acid group here and a carboxylic acid group here. This is called cis because these two groups are on the same side of the double bond, and this is trans because these are on opposite sides of the double bond. Imagine a hydrogen here, whereas the hydrogens would be here in this case. The reason why you would use the maleic anhydride is because it's cheap. It's a very low-cost monomer. But you want the trans isomer because it has a lower energy level, it's a less strained structure than the cis isomer. Also, it's less sterically hindered, so you can get better cross-linking across that double bond. So you can create a situation in which this isomer will rearrange to this one, so you can use the low-cost monomer, but still get the more favorable energy level-wise configuration of the trans isomer. So how do you do that? Well, using maleic anhydride is less costly, but you want that fumarate unsaturation. So you can use propylene glycol to favor a high rate of isomerization. And when you have the trans fumarate isomer, you get more reactivity across the double bond. So they did an example study. So the fumarate ester in the form of ethyl fumarate was 40 times more reactive with vinyl monomers than ethyl malleate. So the malleate ester, 40 times more reactive. So that's why you want the fumarate functionality. And the way you accomplish that is by putting in maleic anhydride in the presence of a secondary glycol. You still get some isomerization with other glycols like ethylene glycol, but it's lower than if you use a secondary glycol. Now this is primary because this is on the end. This is secondary because you have this other bulky methyl group sticking off here. So this is secondary, whereas that is primary. So this is a little more expensive than this, but maleic anhydride is very, very much less expensive than both. So that's why maleic anhydride is isomerized in the presence of propylene glycol to get that fumarate unsaturation. So to kind of show this, how this works, so you have a glycol, and this is your secondary glycol. Your isomerization rate in the presence of propylene is 96%. So if in the presence of the secondary glycol, you get almost all of it turning from the malleate ester into the fumarate ester. So that's pretty good. You can also manipulate the reaction temperature. So the higher the reaction temperature, the more isomerization to fumarate. So you can use a secondary glycol and do it at high temperature, and you get almost all of that maleic anhydride to convert to a fumarate ester, and Bob's your uncle. Everybody gets what they want out of that. Low-cost monomer, lots of fumarate, trans isomer. So there are two steps to polymerization. The first one being polyesterification to synthesize the alkyd, and then a copolymerization of the alkyd with a reactive diluent to form the unsaturated polyester resin. So once again, the alkyd is just the polyester. The unsaturated polyester resin is the alkyd plus a reactive diluent. So It's a polyesterification. This is a condensation reaction carried out in a reactor with an accessory like a condenser to eliminate water. You're creating water as a small molecule, you have to pull that off to get molecular weight to form. And this is usually done under a blanket of inert gas like nitrogen that reduces oxidative destruction of that olefinic double bond. This can be accelerated, so you don't need a catalyst, but it can be accelerated. Again, this is a condensation reaction, so they take a long time. So anything that can help the process along, make it go faster, is good. Mineral acids like sulfuric acid, aryl sulfonic acid, so para-toluene sulfonic acid, dibutyl tin oxide, and other titanates, so tetrabutyl titanate is another one that can be used. Tin compounds offer the best compromise between reaction acceleration and undesirable side effects. So, and the undesirable side effects can be the darker colored resin that can be found with para-toluene sulfonic acid or sulfuric acid. You can also get haze in the resin. The nice thing about unsaturated polyester resins is you can get good clarity, so you want to preserve that. And it's harder to get these acids out of the system at the end, so the tin compounds give you a better balance of that at the end for a catalyst. Once again, you can still do polyesterification without catalyst. So this is your reaction scheme, and this is handy dandy, color coded for your viewing pleasure. So this is your glycol. Again, this is a secondary glycol. Your methyl group is there. This is your maleic anhydride. This is your olefinic unsaturation here. And this is your isophthalic acid. So this gives you water resistance, but it doesn't participate in cross-linking. So this is a terpolymer. You put all these three things together under nitrogen at 200 to 230 degrees Celsius to push all that water off, and you get this particular setup here. So again, OH reacts with carboxylic acid, so you're always going to have some carboxylic acid present and then a glycol. So this one is attached to a glycol, and then this one is attached to a glycol. This isomerases into this. Cis isomer isomerizes in the presence of propylene glycol into the fumarate ester. So that's what we want. We want a lot of this present in the final alkyd. So this is just the alkyd. This is just our polyester alkyd here. But again, green, green, blue, blue, red, red, blue, blue. That's where they come from in the repeat unit. And again, this is a polymer. Why? Because there's an N and a bracket. And look, another bracket. So that is a polyester. So the way you accomplish this is you put all your reactants into the reactor, your glycol, your diacid, any catalysts. You gradually raise the temperature to 140 Celsius with continuous stirring. You reflux these reactants. In other words, you boil them until they are bubbling. Sometimes you use a co-solvent like xylene to help distill the water off. You gradually raise the temperature to 190 Celsius, and you continue this reaction until the acid number of the system is 38 to 45. And what that tells you is the number of unreacted acid units that are still present. And that helps you determine the molecular weight from that acid number. So this is an indication of unreacted acid remaining in the system. We'll do a lab on this, but acid number is expressed as milligrams of KOH, potassium hydroxide, per gram of sample. As the acid number decreases, the viscosity of the system increases, just like the polymer size and molecular weight increases. So if your acid number is going down, your molecular weight and your viscosity are going up. So once you reach that desired acid number and you're just, sticking some sort of thing in that reactor to scoop up a little bit and then go do a titration, you cool the whole system below 150 Celsius. When you get to about 82 to 93 Celsius, you blend that alkyd with a reactive diluent. And that lower temperature is important. You don't want to cool it all the way to room temperature because then it might be a solid. So you want it still to be at elevated temperature so it's somewhat liquid. But you don't want it to be too high because you're adding a potentially flammable reactive diluent to the system. So styrene, methyl methacrylate, dialylphthalate. Once you have that reactive diluent blended in at, when it's warm, then you can cool it all the way down to room temperature. It's customary to use excess glycol because during the process of distilling off water, you can accidentally distill off some of that glycol. So you typically over-index the glycol a little bit so that you can make up for what is lost with the water byproduct during polycondensation. Here's a typical reactor charge for an unsaturated polyester resin. Here's your phthalic anhydride. Again, this is this contributes the carboxylic acid, but not olefinic unsaturation. This is your glycol or your diol. This is your carboxylic acid species that does contribute the olefinic unsaturation. And then here's your hydroquinone, and this is a catalyst. You can tell that by the amount. Then after these are all polymerized, you use styrene monomer, and this makes up about 1 pound of thinned resin at 60% non-volatile material. In other words, 40% styrene. So non-volatile material is the alkyd, 40% styrene is the reactive diluent. So the hydroquinone is actually, sorry, it was not a catalyst, it is a polymerization inhibitor for styrene. So you put a little bit of that in there so that this doesn't, the whole formulation doesn't start to spontaneously react on the shelf. So you take your unsaturated alkyd, you mix it with a reactive diluent, and you can use alkyds for other purposes without the reactive diluent. But typically, to make the entire resin, you mix those two things together. Once again, the alkyd is produced from polyesterification, from propylene glycol, malate, and phthalate monomers. Then your reactive diluent, like styrene, methyl methacrylate, vinyl toluene, butyl acrylate, something with a vinyl group in it, in monomer form is mixed with that as both a solvent and something that can react further. So once again, the overall unsaturated polyester resin is an unsaturated polyester alkyd plus the reactive diluent. The number average molecular weight of your alkyd ranges anywhere from 800 to 3,000, so larger or smaller depending on the application, and you use a low molecular weight reactive diluent. So a small molecule reactive diluent, low molecular weight prepolymer to make your overall resin. Typically styrene is the diluent of choice. It's low cost, it readily copolymerizes with the alkyd at ambient temperature or elevated temperature. It gives low viscosity resins at reasonable monomer levels, and compared to other reactive diluents, I mean not compared to water, but other reactive diluents, it is relatively non-toxic and hypoallergenic. When we're talking about other systems like isocyanates or epoxies, those are highly toxic, and I mean again, this isn't stuff you're going to use as sunscreen, this is just less toxic than other more toxic things. So once again, you're not drinking your unsaturated polyester resin or your reactive diluent. It's just that styrene compared to other things is less toxic. However, there are problems with styrene. It is volatile. It easily evaporates, and there are considerations about what parts per million you can have in the air in the workplace. So 50 to 100 parts per million in the environment. Styrene does have a distinctive smell. And again, if you're smelling it, it's in your bloodstream. The other problem is it has a flash point of 35 degrees Celsius. Now, if you don't think in Celsius, like I don't, when I'm out in, like I'm an American, I'm out in public, outside of my house, I think in Fahrenheit, but 35 Celsius is a warm summer day here in southeast Kansas. So this flash point, it could be above the flash point on a warm summer day. So you have to have DOT labeling that identifies it as flammable, and sometimes you can't get it shipped if it's a really, really hot summer. So it can create a hindrance when you're transporting it, if you have to transport it by truck or certainly by plane. So when you copolymerize, what you get is an addition of the reactive diluent across the fumarate double bond that creates a link between the unsaturated polyester alkyl chains. So here is propylene glycol, fumaric acid, propylene glycol, phthalic acid, propylene glycol, fumaric acid, and in between these fumaric acid unsaturation, that's how the styrene adds across those. So again, here is your key on the bottom, and to put this into a structure form, this is what this looks like. So here in the alkyd, we would have had that double bond prior to free radically polymerizing the styrene. So the styrene adds across this double bond and connects chains this way. So here's my little squiggly chain that shows it's going on to another one, and you have your cross-link here that consists of short chains of polystyrene, linking the two alkyd chains together. When you do that cross-linking reaction, it's initiated by heating a peroxide catalyst to kick off the free radical polymerization. And typically you use excess reactive diluent monomer. The gel point of these occurs about 5% of the carbon-carbon double bond conversion. You get solid at about 50% double bond conversion, and then you get further conversion to about 90 to 95% overall. There are many things you can do to change the properties of the resin to make them higher molecular weight, more flexible, more chemically resistant, more hydrolytically stable, more UV stable, or more flame retardant. And that can be done by choosing different components of either your alkyd monomers or your reactive diluent, and I'll discuss some of those now. So if you use isophthalic acid in place of phthalic anhydride, you get a higher number active molecular weight. So typically 800 to 1,000 for phthalic anhydride, you can get 1,500 to 2,000 for isophthalic acid. So that can create a tougher material, more chemical resistant material, something that's more hydrolytically stable with a higher heat deflection point, as opposed to something that uses phthalic anhydride. Maybe you want something that's more flexible. Instead of using propylene glycol, you use dipropylene glycol or diethylene glycol. Or you use adipic acid in place of phthalic anhydride. And so that gives you better tensile elongation, more flexibility, more toughness. However, when something is more flexible, you decrease the heat deflection temperature and you decrease the chemical resistance. So you have to kind of balance out your properties. You have to optimize for what it is you want for a particular application, like any material. So if I want something to be more flexible, which one of these would I use? So here is propylene glycol, here is dipropylene glycol. Which one of these would I use if I wanted something to be more flexible? The world may never know. Moving on, if I wanted to create if I wanted to make it more flexible by changing my diacid, which one of these would I use? Let's see here. Maybe one with a big long alkyl chain in the middle and does not have this rigid ring structure present in it. So this one for more flexibility in that case. So to increase chemical resistance, hydrolytic stability, UV stabilization, you can use neopentyl glycol in place of propylene glycol. Neopentyl glycol will do this in both phthalic anhydride and isophthalic acid resins, so that is a good choice for your glycol if that's what you're going for. The structure of neopentyl glycol produces a linear alkyd structure, and this has limited compatibility with styrene. So in a way to make this compatible with styrene, you usually limit the use of neopentyl glycol. You mix it with another glycol. So propoxylated bisphenol A, hydrogenated bisphenol A, or 2,2,4-trimethyl-1,3-pentadiol, to make sure that the overall resin is still compatible with styrene as a reactive diluent. To enhance flame retardancy, you put in some halogens. That's kind of the go-to thing. They're trying to get away from that because halogens have some negative effects, but something with bromine or chlorine are usually the way to go. So tetrabromophthalic acid for your diacid, or tetrachlorophthalic acid can be used for your diacid in place of phthalic anhydride. Here's chlorendic anhydride that can also be used to enhance flame retardancy, and dipromoneopentyl glycol, again, it has halogens on it, and that enhances the flame retardancy. So this one gives you dicarboxylic acid, so do these once you open up the anhydride rings, and this can be used as a diol in place of other diols to enhance flame retardancy. So to change your properties, here's what you get when you change your glycol. So propylene glycol, low cost, compatible with styrene. Ethylene glycol, low cost, more rigid. Dipropylene glycol, flexible, tough. Diethylene glycol, same thing. Neopentyl glycol, better UV, water, and chemical resistance. Trimethylpentadiol, water and chemical resistance. Cyclohexane dimethanol, better electrical properties. Propoxylated bisphenol A or hydrogenated bisphenol A, water and chemical resistance. And then dibromoneopentyl glycol, enhanced flame retardants. But wait, you can also do similar things with the acids. So phthalic anhydride is usually your go-to, along with maleic anhydride. Those are your lowest cost and styrene compatible or with unsaturation. You can add adipic acid in place of your phthalic anhydride to get more flexibility and toughness. You can also use isophthalic acid for better toughness, water, and chemical resistance. Terephthalic acid can give you a higher heat deflection point. You can use fumaric acid instead of maleic anhydride for maximum reactive unsaturation, so you already have that fumarate ester present because you're using fumaric acid. Glutaric acid, flexibility and toughness, same thing with dimer acids or azelaic acid. Chlorendic acid, flame retardance and chemical resistance, same things with tetrabromophthalic anhydride and tetrachlorophthalic anhydride. And then if you require air drying properties, and some of these do, you use endomethylene tetrahydrophthalic anhydride. I deserve a gold star for being able to say that. Again, you have choices with your reactive diluent to enhance properties. Methyl methacrylate gives you better weather resistance over styrene. Same thing with butyl acrylate or butyl methacrylate. They don't yellow. You can use alpha-methylstyrene. This gives you a cooler cure and a reduced exotherm. Once again, cross-linking is exothermic. You need to control that. Vinyl toluene is lower volatile and has a higher flash point. So same thing with paramethylstyrene. Diallyl phthalate and diallyl isophthalate are very low volatility and are useful in prepregs. Octyl acrylamide has a solid monomer, so it's useful for molding compounds. You also have trimethyl propane triacrylate, and that gives UV and electron beam curing, so very fancy. Triallyl cyanurate, triallyl isocyanurate, and diallyl malleate give you good high heat deflection temperature, and diallyl tetrabromophthalate gives you high heat deflection temperature and enhanced flame retardants. So from this point, after this, we will have another unsaturated polyester resin applications lecture. Please do the quiz that's associated with Unsaturated Polyester Resins Lecture 2 before you move on to the third Unsaturated Polyester Resins Lecture 3.